Hello students, welcome to the third part of our topic Strand 2.1, which is atomic structure and bonding. Now in this session we are going to be discussing about the trends in the periodic table. So when we are talking about periodic trends, we are looking at specific patterns which are present in the periodic table, which show different aspects of a certain element. The major periodic trend that we are going to be studying this year are electronegativity, ionization energy, atomic radii, and ionic radii. So let's try to understand why these particular trends exist. We are going to be using two important terms to describe these periodic trends. The first one is called effective nuclear attraction. This is where the electrons are attracted to the protons which is in the nucleus of an atom. Now, if we are looking at a particular trend going across a period, one thing that is very common, like say for example, we look at group period 2, the number of shells will remain the same. So that simply means that no new electrons or no new shells are being added as we are looking at the trend going across. So as we move from left to right, the number of electrons and protons increase. This in turn is going to increase the attraction the electrons have for the protons. So the greater the attraction is, the stronger the grip of the electrons will be. The electrons will be held more closely towards the protons. And as a result, when we're looking at one example, let's say beryllium. Beryllium is in period 2. Okay. So if you're looking at the atomic radii of beryllium and compare it to oxygen, notice that both of these elements belong to period 2. However, oxygen is having a smaller atomic radii. And the reason why that happens is the number of electrons around beryllium is 4, while the number of electrons around oxygen is 8. Okay, so there is more attraction between the electrons and the protons in oxygen. That's why the electrons are pulled in closer. Okay, so the atomic radii is going to decrease. While in beryllium, the attraction between the electron and proton is there, but not as much as in oxygen. And as a result, the atomic radii is slightly bigger than that of oxygen. So that basically explains why going across the period, the size of the atom is going to get smaller. And that we are going to be looking at in the next bit. Then we look at another definition, which is called shielding effect, also known as a screening effect. Now, in the shielding effect, the inner electrons or the co-electrons, they will shield or prevent the outer electrons from receiving any effective nuclear attraction. So we are going to explain this by looking at the trend going down. As we're looking at the periodic trend down the group, we will notice that there is an addition of a new shell. Unlike the periodic trend going across, we didn't see a new shell. Electrons were added in the same shell. But when we go down the group, the electrons are added in a new shell. When that happens, the inner electrons which are in the inner shell, they form a barrier, okay, a shield. And that shield will prevent the attraction between the valence electron and the protons. As a result, the electrons and protons which are not very much attracted to each other, they are pulled away from each other. So the radii is going to expand, is going to increase. Okay, so you are expected to know the definition of effective nuclear attraction, which is the attraction between the electrons and the protons, and shielding effect, which is a repulsion force that is created by the inner electrons. So the inner electrons will try to push away the outer electrons. Okay, they will push the outer electrons away. And when that happens, the outer electrons doesn't get any attraction with the center, which is the protons. So we will be looking at the general trend in the periodic table in terms of atomic radii, ionic radii, electronegativity, ionization energy, both across the period as well as going down the group. So let's try to understand the atomic radii in the periodic table. When we are looking at the atomic radii, notice how the size of the atom is getting smaller. Across the period, the atoms are getting smaller. And the reason why the atoms are getting smaller as we go down, as we go across the period, is because since electrons are added in the same shell, there is a greater attraction between the electrons and the protons, which is called an increasing effective nuclear attraction. So when we are looking at the atom which is right on the right hand side, like fluorine and neon, these atoms will have a greater effective nuclear attraction because they contain more electrons and protons. Now when we go down the group, you can see that the atoms are getting larger. Now the reason why these atoms are getting larger is because the electrons are added in a new shell. And when that happens, then the inner electrons will repel the outer electrons. They push the outer electrons away. And as a result, the outer electron drifts away because it doesn't get a lot of effective nuclear attraction. And that repulsion is known as a shielding effect. So going down the group, there is an increase in the shielding effect, which makes the radii of the atom get bigger. So let's try to watch a short video and try to understand how atomic radii is affected across and
When we visualize an atom, we frequently think of the electrons traveling in fixed orbits around the nucleus. However, it's important to remember that the electrons travel in orbitals. These orbitals are not well-defined boundaries, they simply illustrate the probability distributions of where the electrons are most likely to be found. Atomic orbitals come in a wide array of complex and beautiful shapes depending on their electron configurations. Although the shapes of atomic orbitals are diverse, we're going to use a simplified model to explore how and why the atomic radius changes. The atomic radius is a measure of the typical distance from the center of the nucleus to the boundary of the surrounding cloud of electrons. It's affected by the number of protons and electrons that make up an atom. Both change in predictable ways throughout the periodic table. Let's take a look at group trends first. As you travel down a group, you are adding electrons to energy levels that are farther away from the nucleus. All elements in group 1 have one valence electron, but different electron configurations based on their period. Hydrogen is in the first period, which means it has one electron shell. Its atomic number is 1, which means a neutral atom of hydrogen has one electron. Lithium is in period 2, which means it has 2 electron shells. Its atomic number is 3, so a neutral lithium ions configuration looks like this. Sodium has 3 electron shells. Its atomic number is 11, so a neutral atom has 11 electrons. As you continue down the group, the atomic radius continues to increase due to the increase in electron shells. Now let's examine trends across periods. As you are traveling across a period from left to right, the atomic radius decreases due to the effective nuclear charge and electron shielding. We're going to compare lithium and beryllium to gain a better understanding of how these processes affect atomic radius. Lithium has an atomic number of 3. This means a neutral atom of lithium will have 3 protons and 3 electrons. There are 2 electrons in the inner shell and 1 in the outer shell. The positively charged protons pull in the negatively charged electrons. At the same time, the inner shell electrons repel the outer shell electrons because they have the same charge. This is called electron shielding. When we move from lithium to beryllium, we gain 1 proton and 1 electron. It's important to note that outer shell electrons do not shield the other electrons. That means that beryllium has the same number of electrons shielding as lithium does. However, beryllium does have a higher effective nuclear charge because of that additional proton. This increased positive charge in the nucleus causes electrons to be pulled in more strongly, resulting in a smaller atomic radius. So as you continue to travel across the period, the atomic radius continues to decrease. As you can see from the examples provided, the atomic radii change in predictable ways throughout the periodic table.
Let's look at the trend of ionic radii. Ions are particles which are formed when an atom loses or gains electron. When an atom loses electron, it forms cations, which are known as positive ions. Now, when cations are formed, the remaining electrons are more closely attracted to the nucleus, which means that there will be a greater effective nuclear attraction. Therefore, the size of the cation will be smaller than the atom it is made from. Let's look at some examples here. Let's compare the size of lithium atom and lithium ion. Between lithium atom and lithium ion is far more smaller than the atom. Likewise, when we compare all the cations given here, they are smaller than the atom. And the reason is because these ions have a greater effective nuclear attraction. Anions are particles which are made when an atom gains electron. So when an atom gains electron, it forms negative ions, which are known as anions. Now remember, there is an addition of a new electron. So when there is an addition of an electron, the inner electrons will repel that. Okay, the inner electron doesn't want that electron. It kind of repels it, moves the electron away from it. And as a result, when the electron moves away, there is less effective nuclear attraction. But there is more shielding effect, which is a repelling effect. Now, because there is more shielding effect in the anion, the size of the anion is going to increase. So anions are bigger than the atoms they are made from. Let's say, for instance, we look at all the halogens. When these halogens form anions, there is a gain of electron. Okay, so the inner electrons will be repelling that added electron. So that added electron will be moved far away. It has less effective nuclear attraction now and more shielding effect. That is why these anions are bigger than the atoms. The third trend in the periodic table is electronegativity. As you look across a period and down the group, you will see that electronegativity increases across and decreases down the group. Electronegativity is the attraction an atom has for the shared pair of electrons. So when we look at hydrogen and chlorine as an example, between hydrogen and chlorine, there is one pair of electrons being shared. So hydrogen will share one electron and chlorine will also share one electron. And then there are lone pair of electrons around the chlorine atom. So these electrons which are found between H and Cl, they are known as a shared pair of electrons. Now chlorine, because it is more electronegative than hydrogen. Now before we continue, as we are looking across a period, the electronegativity is increasing because across a period there is increase in effective nuclear attraction. While going down the group, the electronegativity is decreasing because there is an increasing shielding effect. So when we're looking at the trend, chlorine is far more electronegative than hydrogen, and as a result, it will attract these shared pair of electrons more towards itself. As a result, chlorine will get a slight negative charge while hydrogen gets a slight positive charge. The fourth trend in the periodic table is called the ionization energy. This is the minimum energy required to remove an electron from an atom in the gaseous state. Now, the kind of atom that loses electron are metals. Metals lose electrons. So when we're looking at the trend in the periodic table, going across the periodic table, the ionization energy is increasing. Okay, let's look at an example here. So in both the cases, the elements are in the same period. Okay, both have the same number of shells. But in lithium, that valence electron is far away from the center. Electron here, that valence electron is not that much attracted to the center. So it will be easy to remove this electron. Okay, so this is the electron that will be easily removed because there is less attraction between that electron and the proton. So it will require less energy. Requiring less energy simply means low ionization energy. Now, when we're looking at the valence electron for nitrogen, in nitrogen, this valence electron is very strongly bonded or very strongly attracted to the protons. And that strong attraction will make it harder to remove the electron. That means it will require a lot of energy to remove that electron. So the ionization energy is going to increase. So generally we can say that going across the periodic table, the ionization energy is increasing because there is an increased attraction between the electron and the proton. And that is called an increase in the effective nuclear attraction. Now when we're looking at the trend going down the group, the ionization energy is going to decrease. And this is the reason why it happens. If you look at the trend going down the group, you will notice that there is an addition of a new shell. So the inner electrons, they will try to shield the outer one. By doing that, we simply means that these inner electrons will repel the outer electron. So the outer electron will be moved away. And when that happens, there will be less attraction between this outer electron and the proton. So when the attraction is lesser, it will be easy to remove the electron from the atom in the gaseous state. That means it will require less energy. So the ionization energy is going to decrease. Now, generally we said that across the period, ionization energy increases. And this we said was because going across the period, effective nuclear attraction increases. That means that the electrons are more closely attracted to the proton. If the attraction is greater, it will be difficult to remove the electron from the atom, which means the ionization energy is going to be more. However, when we look at our graph, this is what we get. Instead of having a general trend as we expected, there are some trends which do not actually follow the pattern. Like for instance, atomic number 4 and atomic number 5. By right, we expect atomic 5 to have a higher ionization energy. But here we are seeing that it's the opposite case. So let's try to understand why there is a fluctuation in the ionization energy here. And to explain that, we are going to be looking at the stability of the valence orbital. So let's look at atomic number 4. Atomic number 4 is beryllium. Beryllium's configuration is 1s2, 2s2. So we will be looking at the valence shell, which is a 2s orbital. So 2s orbital, this is what it is, 2s2, 2 electrons are fully filled. Let's look at atomic number 5. So atomic number 5 is boron. Okay, that's the configuration of boron, 1s2, 2s2, 2p6. So let's try to look at the valence orbital, which is the p orbital. So there are 3 of that. Okay, so that's 2p1. Now, in order for the electron to be lost from the atom, that you understand that the first IE means the last electron to be lost. So in beryllium, this is the last electron that is going to be removed. When we talk about the first ionization energy of boron, then this is the electron that is going to be lost. So last in, first one to go out. That's the procedure. Okay, so whichever was the last electron you filled, that will be the first one to be lost. So once the last electron is removed, which is called the first ionization energy, then the second last electron will be lost. So the energy required to remove the second last electron will be known as the second ionization energy. Now look at the orbital stability of both these atoms. For beryllium, okay, this particular atom is actually coming from a fully filled orbital, and for boron, that is the orbital, okay, which is losing the electron. So for beryllium, this electron is coming from a fully filled stable orbital, which is why the first ionization energy will be higher. For boron, this is the electron that is going to be removed, the one circled in green, and this electron is coming from a partially filled orbital, which is unstable, so the ionization energy is going to be lower. Once again, the first ionization energy is the minimum energy required to remove the last electron from the atom in the gaseous state. Okay, let's look at some more examples. So we have a fluctuation here in atomic number 7 and atomic number 8. So between atomic 7 and atomic 8, let's see what these atoms are. Okay, atomic 7 is nitrogen, whose configuration is 1s2, 2s2, and 2p3. So let's look at the valence orbital, which is 2p3. So this is how the three orbitals are placed. While in oxygen, which is atomic number 8, you have the configuration of 2p4. Okay, so we have a 2p4 here. Okay, now let's see which electron is going to be lost from nitrogen. Now, first IE means the last electron being lost. So in nitrogen, this is the last electron, and this last electron is coming from a half-filled stable orbital. Remember, the most stable orbital is the one that is fully filled, followed by half-filled, and then the least stable will be the partially filled. So this is the reason why the first ionization energy of nitrogen is higher. When we look at oxygen, this is the electron that is going to be lost, and this electron is coming from a partially filled unstable orbital. That means the ionization energy is going to be lower. In a similar way, you can see that there are a lot of other fluctuations between atomic 12 and atomic 13, between 15 and 16. You can use the same concept of the stability of orbital to explain why there is a fluctuation in between these two atoms. So students, it's that time of the session again where we are going to have a quiz. Let's see how much you have understood the topic on Strand 2.1 on periodic trends. So question 1 for the session is, arrange the following atoms in their atomic radii from the smallest to the largest. You can pause the video and check your answers. So the correct answer is fluorine, smallest, which is smaller than carbon, that is smaller than bromine, and then the largest atom is gallium. Question number 2. Explain why chloride ion is larger than the chlorine atom. So, chloride ion has a lot of shielding effect due to the extra electrons. Therefore, the effective nuclear attraction in the chloride ion will be lesser compared to that of chlorine atom. And when the effective nuclear attraction is less, that simply means there is more shielding effect and the size of the atom or the ion will be larger. So students, I hope you have enjoyed the session. We will meet in the next part where we are going to be discussing about chemical bonding. Until then, take care. Bye.